Alright, so we are still on past question review on Maths 305. This is actually question 1 of the 2021 Maths 305 exam question from Rivers State University, Port Harcourt, Nigeria. So the first question says, state without proof the Cauchy's integral formula and hence evaluate the integral cos pi z squared all over x minus 1 multiplying x minus 2 all squared times dz. So that's the A, where C is the cycle, Z equals 3. So that's the first part of that question. That's question 1A. Whereas the B part says evaluate integral from 0 to I plus 1 of x squared minus iy multiplies the z along the path I y equals x, I y equals x to the power of 2. So let's start with the A part of the question. Alright, the first part says we should state without proof the Cauchy's integral formula. The Cauchy's integral formula is given as integral of f of z, the z is equal to 2 pi I. Okay, integral of f of z dz all over z minus z naught, please, is equal to 2 pi I multiplied by f of z naught, where f of z naught simply means the function identified at the pole. Z naught simply stands for the pole. That's the Cauchy's integral formula. Now we are given to evaluate this integral. So obviously we are going to be using the Cauchy's integral formula to solve this question. Mind you, you can also use the residue formula, the Cauchy's residue formula, to solve this same problem. So for more understanding of the Cauchy's residue formula, you can go through my series on complex analysis, find the Cauchy's residue formula, and of course you can be able to solve this problem using the Cauchy's residue formula. But let's use the integral formula. Okay, now you are given integral, you are given to evaluate integral of this function, but then we are given a cycle. So the cycle was given to us z to be equal to 3. Now this simply means z plus 0 is equal to 3. Now where 0 is the center of the cycle and 3 is the radius of the cycle. So we are going to now plot the cycle first, then calculate our poles and see if they fall in the cycle. Or before drawing the cycle, let's find our poles. To find your poles, you have to first of all equate the denominator of the given integral to 0. So we have to equate these whole denominators now to 0 to obtain the poles. Alright. To find pole, therefore, we put in z minus 1 multiplying z minus 2 all squared to be equal to 0. So we simply equate the denominators to 0. If we do that, this simply implies that z minus 1 is equal to 0, or z minus 2 all squared is equal to 0. Now, if z minus 1 is equal to 0, you can send negative 1 over to this side of the equation. This simply implies that z is equal to 1. Or again, from here, z minus 2 squared is equal to 0. This simply implies that z minus 2 is equal to, you simply take the square root of 0. That still gives you what? 0. And therefore you have z to be equal to, send minus 2 over to this side of the equation. Then you have that z is equal to 2. So the poles are z equals 1 and 2. These are our poles. Now we need to plot the cycle and confirm that the poles fall within the cycle. So from the cycle you are given z plus 0 equals 3. So I explained that 0 is the center of the cycle, whereas 3 is the radius of the cycle. So you plot your cycle and you have this. Now this is the origin of the cycle. This is your complex plane. This is the origin, which is 0. You have here to be 1. You have here to be 2. You have here to be 3. So measure out basically the radius of the cycle, which is 3. Similarly, this is going to be negative 1. This is going to be negative 2.
and this is going to be negative 3. So this is now, since this is negative 3, which is reduced, this is also positive 3, then you plot your cycle connecting the negative 3 and the positive 3 since the radius of the cycle is 3. So you have simply this. Alright, so these are cycle. Then we check if the poles falls within the cycle. So the given poles are z equals 1, and if you look inside the cycle, we have 1. So 1 falls inside the cycle. We also have z equal to 2 for the poles. So you find out that 1 and 2 actually falls within the cycle. So which means we are going to be what? Solving for the both poles, 1 and 2. Okay, so let's pull out the integral once more. We have integral of cos pi z squared dz all over z minus 1 multiply z minus 2 all squared. Now, you want to solve for this function, so you consider the first pole. For the first pole, for pole z equals 1. So you look at this integral. If I put in 1 in place of z here, I'm going to be having 1 minus 1, which makes everything at the denominator to be 0. So what I will do is I'm going to be dividing top and bottom of this equation by the value at the denominator, where when I put in the value of z as 1, I'm not going to be obtaining 0. If I put in z here as 1, this becomes 1 minus 2. And 1 minus 2 will give me minus 1 and not 0. So for that reason, I will divide top and bottom by z minus 2 to the power of 2. Okay, so this is going to now be integral of cos pi z squared dz divided by z minus 2 to the power of 2 all over z minus 1 times z minus 1 all squared divides z minus 1 minus 2, please, minus 2 all squared. So you simply have this. So from here, z minus 2 squared simply cancels z minus 2 squared. This integral becomes integral. I have cos pi z squared times dz all over z minus 2 all squared all over. Now I am left here with z minus 1. So comparing this with the Cauchy's integral formula, the Cauchy's integral formula simply states that, okay, we have the integral of f of z dz all over z minus z naught. You have this. So upon comparison, you have the integral sign, you have z minus z naught, which appears at the denominator. Then that means at the denominator here we have z minus 1. So this z minus 1 corresponds to z minus z naught. The integral sign corresponds to the integral sign. I have the z here, the z corresponds to this dz. So which means what I have left is f of z under this Cauchy's integral. That means my f of z, which is the function, simply means everything here apart from the z, this integral, and what, this denominator, because this denominator corresponds to this denominator. The z corresponds to the z, integral corresponds to integral. So this means f of z corresponds to every other thing here. So that simply means that my function, this implies that f of z is going to be equal to cos pi z squared all over z minus 2 all squared, and you have this. Now you find the function at the pole. So remember, we are considering pole when z is equal to 1. So for z equal to 1, for z equals 1, therefore you find f of 1. That means putting the value of z as 1 into this function anywhere you find the value of z. So f of 1 now becomes, I have cos pi z squared, and z is equal to 1, so 1 squared all over z minus 2. Z now is 1, so it becomes 1 minus 2 all squared. So this is equal to, of course, 1 squared is 1, so I'm left with cos pi all over 1 minus 2 is minus 1, minus 1 squared simply gives me 1. So this simply means that f of 1 is going to be equal to cos pi approximately. And pi in front of a trig function, pi always appears as 180. So this is invariably saying cos 180, and the result is equal to minus 1. So for the first pole, of course, we have f of 1 to be equal to minus 1. But from Cauchy's integral formula, you know, integral of f of z dz all over z minus z naught, we simply said it is 2 pi I multiplied by f of 1. So this is going to be equal to 2, sorry, f of z naught. So this is going to be equal to 2 pi I multiplies, for the first pole, f of 1 simply give me what? Negative 1. So multiply by negative 1. So this is now going to be equal to what? Minus 2 pi I. So you keep this aside. This is now for the first pole. Now let's fall back to our original integral. So this is the original integral given to us. Now we are considering when z is equal to 2. That is now for the second pole. So you observe that if you put in the value of z here as 2, 2 minus 2 becomes 0. Automatically, everything at the denominator will become 0. So which means this division will give us an infinite value. So for that reason, you have to now divide through by the function in which when you put in the value of z as 2, you are not going to obtain 0 at the denominator. And that is simply putting in z as 2. I have 2 minus 1 gives me 1. So it means I'm going to be dividing top and bottom by z minus 1. So this integral simply becomes integral of cos pi z squared dz all over z minus 1 all over z minus 1 multiply z minus 2 all squared all over z minus 1. So you observe that z minus 1 strikes z minus 1 here. So therefore, this integral becomes integral of cos pi z squared multiplies the z all over, we have z minus 1 all over z minus 2 all squared. Once again, you recall now the Cauchy's integral formula, or the Cauchy's integral itself, and that is simply integral of f of z dz all over z minus z naught. So once again, z minus z naught is denominator. This corresponds to this z minus 2 to the power of 2. So that means this goes for the denominator, this integral goes for this integral, the z goes for the z. So it means that what I am left now with is the function f of z. That means my function f of z becomes everything here aside the z, aside the integral sign, and aside the denominator. Alright, so this simply implies that my function f of z is equal to cos pi z squared all over z minus 1. So you find the function at the pole. Okay, so you find the function at the pole. Okay, now at z equals 2, this is now the second pole. At z is equal to 2, so wherever you see z, put in the value as 2. This becomes f of 2, and that's equal to, I have cos pi z squared. This is cos pi, z itself is 2, so that becomes 2 all squared all over, I have z minus 1 here, and z is 2, so I have 2 minus 1. This is now going to be cos 2 squared is 4, so that becomes cos 4 pi all over 2 minus 1 is 1. This remains cos 4 pi. Now in front of a trig function, pi appears as 180. That means 4 pi becomes 4 times 180. So this implies that f of 2 is equal to cos 4 times 180, which is equal to, that's equal to cos 720. So we simply find the value of cos 720. So this simply implies that f of 2 is equal to cos 720 simply gives us 1. Okay, cos 720 gives us 1. So if this is the value, then we find from Cauchy's integral formula, therefore integral of f of z dz all over z minus z naught, we said is simply 2 pi I multiplied by f of z naught, where f of z naught simply means the function at the pole, which we just obtain here as 1, and this is going to be equal to 2 pi I multiplied by 1. So this integral is simply going to be what? 2 pi I. Now, since we've obtained the two values, then total integral, therefore integral of f of z dz all over z minus z naught is going to be, we sum the two values up. Remember, for the first case, one we obtain when the pole was 1, and then for this case, when the pole was 2, we add them all up together. So when the pole was 1, we had minus 2 pi I. When the pole was 1, we had minus 2 pi I. So we simply add them all up together. So we had minus 2 pi I. Now when the pole was 2, we had 2 pi I. So we add plus 2 pi I. So the answer is simply equal to 0. So for that question, that integral is simply equal to 0. Now let's consider the B part of the question. The B part of the question says evaluate integral from 0 to I plus 1 of x squared minus iy multiplied by dz. Okay, along the path I, y equal to x, and I, y equals x squared. Okay, so given integral from 0 to I plus 1 of x squared plus iy multiplied by dz. Okay, now this is actually a question on complex integration. And for every complex integration, I always say you let z to be equal to x plus I y. So if z is x plus I y, then we need to find what then is the z. Therefore, the z is equal to, that means differentiate x, so we have the x plus I dy. So the z simply means differentiate each of these terms involved there. So the z equals the x plus I dy. Okay, so in place of the z here, we are going to be plugging this. Aside that, we are given the first condition, let y be equal to x. So we are going to be changing everything in terms of x. If y is equal to x, let's pick out the first condition now. When y equals x, this simply implies that the y will be equal to the x. So where I have I dy, that means the y becomes what? The x. This is going to now become what? I dx, because the y is equal to the x. So therefore, that means that my dz, okay, this means that the z is now going to be equal to, we said, dx. So you have dx plus I in place of the y there. The y is same as the x, so it becomes I dx. Okay, so I am now going to plug this into this integral. So this becomes integral from 0 to I plus 1 of, this is x squared plus iy, but y is equal to x. Remember, we are considering the first case now when y is equal to x. So in place of y, we put in the value as x. So this becomes I x, okay, times dz. Dz now is simply the x plus I dx. So we'll have times the x plus I dx, and we have this. So we are simply going to expand that bracket now. Okay, so if we do that, we are going to have integral from 0 to I plus 1. Let's now expand. So we simply use x squared to multiply everything in the bracket. So I have x squared multiplying the x plus I dy plus, then I will use ix to also expand the bracket. So I have plus ix multiplying the x plus I dy. Okay, so integral from 0 to I plus 1 will now become x squared times the x. This gives us x squared the x plus x squared times I dy. This gives us I x squared dy. Okay, plus ix multiplies the x. Sorry, so this is the x, please, and not the y. Oh, all right, guys, so this is the x actually. So I have x squared, this is the x. So x squared times the x gives us x squared dx, and then x squared multiplies I dx gives us x squared dx, I x squared dx. Okay, plus now ix multiplies the x, this gives us I x dx, plus I times I here gives us I squared. Okay, x times the x, sorry guys, this is the x please and not the y. So x times the x simply gives us x the x. All right, so we simply have this. Okay, so integral from 0 to I plus 1. So we have x squared dx. Let's see if we can collect like terms. Okay, x squared dx. I have I x squared dx. Okay, and I have I x dx over here. So I is common between these two. So this is plus factor I into x squared dx plus x dx. All right. Now over here, I squared from complex number, I squared is minus 1. So this becomes minus x dx. And you have this. Okay, so let's bring the real parts together and the imaginary parts together. This is now integral from 0 to I plus 1. So I simply have x squared, okay, minus x multiplied by the x. Of course, the x is common between these two. These are the real parts. Okay, plus also the x is common here. So I have I into x squared plus x multiplied by the x. Okay, so we'll have this. All right, so we simply integrate the real part separately and integrate the imaginary part separately, or we can even integrate individually. Okay, so this is now integral from 0 to I plus 1 of x squared minus x dx plus I integral from 0 to I plus 1 of x squared plus x dx. So you see now that everything has transposed in terms of the x. So we can easily carry out our integration. So if we integrate x squared, this becomes x to the power of 3 all over 3 minus, if we integrate x, we have x to the power of 2 all over 2. Our limit is from 0 to I plus 1 plus we have I into, similarly if we integrate x squared, we'll have x to the power of 3 all over 3 plus, if we integrate x, we'll have x to the power of 2 all over 2. Limit is from 0 to I plus 1. All right.
So next thing now is to plug in the limit of the integration.
So if we plug in the limit, we are going to have upper limit minus lower limit wherever you see x. So for the first case, we have, in place of x cubed, upper limit is I plus 1. So we have I plus 1 to the power of 3. Okay, minus lower limit. So we have 0 to the power of 3. And 0 to the power of 3 remains 0. So we can neglect that, all over 3. Minus same thing here, in place of x squared, upper limit minus lower limit. So upper limit is I plus 1 all squared. Okay, minus lower limit is 0 to the power of 2, which remains 0. So we can neglect that, all over 2. Okay, plus I into, same thing happens here, upper limit minus lower limit. So upper limit is I plus 1 all squared, all cube, all over 3, plus, in place of x squared, also I plus 1 all squared all over 2, and we have this. So all we need to do now is expand I plus 1 cube and expand I plus 1 squared. Okay, so I plus 1 to the power of 3 simply gives us I cube plus 3I squared plus 3I plus 1. Not forgetting, from complex number, I to the power of 3 is actually minus I, and I squared is actually minus 1. So this simply implies that I plus 1 to the power of 3 is going to be equal to I cube is minus I plus 3I squared. This becomes 3 into I squared is minus 1 plus 3I plus 1. So this is going to be equal to minus I minus 3 plus 3I plus 1. Okay, so we simply have minus I plus 3I. That becomes 3I minus I. That gives us 2I minus 3 plus 1. That gives us minus 2. So this simply implies that I plus 1 to the power of 3 is actually 2I minus 2. So you keep that aside. Next we find I plus 1 all squared. Okay, so I plus 1 squared simply gives us I squared plus 2I plus 1, where I squared is minus 1. So this is actually equal to minus 1 plus 2I plus 1. So minus 1 plus 1 is 0. This simply implies that I plus 1 all squared is equal to simply 2I. So recalling we had this for our integral. So let's put in the values of this expansion into this result of the integral. So we are going to be having, so in place of I plus 1 cube, I plus 1 cube gave us 2I minus 2. So we have 2I minus 2 all over 3 plus, in place of I plus 1 squared, we had 2I all over 2. Okay, same thing here, plus I into, this is 2I minus 2 all over 3 plus 2I all over 2, and we have this. All right, so we can further break this down to be 2I over 3 minus 2 over 3 plus 2 over 2 is 1, so we have I, okay, plus I into, this is 2I over 3 minus 2 over 3 plus 2 over 2 here is 1, so we're left with I. Okay, so this becomes 2I over 3 plus I. So we're adding, of course, the imaginary parts now. 2I over 3 plus I. That gives us 5I all over 3 minus 2 all over 3. So this plus I into, similarly, 2I over 3 plus I. That gives us 5I over 3. This is minus 2 all over 3. So we can expand with this imaginary number here, I. Okay, so this becomes 5I all over 3 minus 2 all over 3 plus, now I, now 5I over 3 multiplies I times I is I squared, so we have 5I squared all over 3 minus I times 2 all over 3 here gives us 2I all over 3. So this is going to be equal to, we have 5I over 3, 5I all over 3 minus 2 all over 3. Mind you, I squared is negative 1. So negative 1 times 5 over 3 becomes negative 5 over 3. So we'll have minus 5 all over 3. Over here we'll have minus 2I all over 3. So let's bring the imaginary parts together. We have 5I over 3. We have here minus 2I all over 3. Then bring the real parts together. For the real parts, we have minus 2 over 3, minus 2 over 3, and then we'll have minus 5 over 3, minus 5 all over 3. So this is going to be equal to, of course, the LCM between these two is 3. or the LCM between all of them is 3. So we can simply take LCM of all. So we have 5I minus 2I minus 2 minus 5. So this is going to be equal to 5I minus 2I, that gives us 3I, minus 2 minus 5, that gives us minus 7 all over 3. So the result can be evaluated further as 3I all over 3 minus 7 all over 3. And that's the value of that integral when x is equal to, or when y is equal to x. This becomes the result of that integral. Okay. Okay, so now we are considering the second part of the question. This is still the integral. Now we are given when y is equal to x squared. Okay, not forgetting earlier we obtained the z to be equal to the x plus I dy. So once again, we make everything to be in terms of x. So wherever you see y, put in the value simply as x squared. Okay, and as such, let's find the y. Okay, let's find the y from here. We are going to have that dy is equal to, this is 2x multiplies the x. So that simply means under this integral, I am going to now be putting in place of the y simply becomes what? 2x dx. So this simply implies that my dz is going to now be equal to dx plus I, in place of the y, I have I 2x dx. So everything now is now in terms of x. Similarly, I'm going to be changing the integral. This becomes integral from 0 to I plus 1. Now I have x squared plus I y, but y is equal to x squared. So that becomes I x squared times dz, and dz is equal to this multiplies the x plus I 2x dx. So I have this. Okay, so I'm now going to be expanding each of the brackets using everything I have here. So therefore, this is now integral from 0 to I plus 1. So I will use x squared to expand this bracket. So x squared times dx plus I 2x dx. Okay, plus I will use ix squared to expand this bracket. So I have I x squared multiplies dx plus I 2x dx. So you see that this automatically changes everything to be in terms of the x or in terms of x, so I can easily integrate that integral with respect to x. Okay, so let's expand now. Integral from 0 to I plus 1. So we simply have x squared times the x. This gives us x squared dx plus x squared times I 2x dx. X squared times 2x here gives us, this is I 2x cubed multiplies the x. Okay, plus now I have x squared times the x, or I x squared times the x. This gives me I x squared the x, plus I have I times I here is I squared, x squared times 2x the x. This gives me 2x cubed multiplied by the x. We have this. Okay, so this is integral from 0 to I plus 1. So let's collect the real parts together and the imaginary parts together. I have x squared. I have x squared dx. This is a real part. And okay, this is x squared dx plus this is I 2x cubed dx. This is plus I x squared dx. Now I squared is negative 1. Okay, so we have minus 2x cubed dx. Okay, so integral from 0 to I plus 1. is now going to be, let's collect all the real parts. I have x squared dx, I have minus 2x cubed dx. These are real parts, so collect them together. This is x squared minus 2x cubed times the x. Collecting the imaginary parts together, so I have plus I into, this is 2x cubed, okay, plus x squared dx, multiply all through by the x, and we have this. All right, so we can easily integrate this separately, the real parts and the imaginary parts separately. This becomes integral from 0 to I plus 1 of x squared minus 2x cubed dx plus I integral from 0 to I plus 1 of, this is 2x cubed minus x squared times dx. So let's integrate now. So I'm going to have, if I integrate x squared, this gives me x cubed all over 3 minus, this is 2. If I integrate x cubed, I'll have 2x to the power of 4 all over 4 from 0 to I plus 1 plus I into, if I integrate x cubed over here, this becomes 2x to the power of 4 all over 4 minus, if I integrate x squared, I have x cubed all over 3. Limit is from 0 to I plus 1. Okay, so this is actually x cubed over 3 minus, of course, 2 goes into 4. 2 into 2 is 1, 2 into 4 is 2. So I have x4 all over 2 from 0 I plus 1, okay, plus I into, same thing here, 2 goes into 2 is 1, 2 goes into 4 is 2. So I have x to the power of 4 all over 2 minus x to the power of 3 all over 3. Limit is from 0 to I plus 1. So we now put in our limits, upper limit minus lower limit. So we are simply going to have, putting in the limits now. So we have, this is x to the power of 4. So it's supposed to be upper limit minus lower limit, but remember that lower limit is 0. So if we put in the value of 0, it still remains 0. So we can only use the upper limit to save time. So x to the power of 3 simply becomes upper limit, which is I plus 1 to the power of 3. So we put in the limits now. In place of x to the power of 3, upper limit is I plus 1 to the power of 3 all over 3 minus, we have, in place of x to the power of 4, we have I plus 1 to the power of 4 all over 2. So observe that we've neglected 0, because if you put in the lower limit as 0 to the power of 3, it still remains 0. So that one is discarded. So we can do with the upper limit alone. Alright, so over here, same thing, we have x to the power of 4. So in place of it, upper limit, I plus 1 to the power of 4 all over 2 minus x to the power of 3, we have I plus 1 to the power of 3 all over 3. So what we'll do now is to find the expansion values of I plus 1 to the power of 4 and I plus 1 to the power of 3. So let's do it and see. So recall earlier we obtained the expansion of I plus 1 to the power of 3. That gives us 2I minus 2. And now also the expansion of I plus 1 to the power of 4 simply gives us this I4 plus 4I to the power of 3 plus 6I to the power of 2 plus 4I plus 1. Okay, keeping in mind that I to the power of 4 is something as I squared times I squared, and I squared is minus 1. So you have minus 1 times minus 1. That simply gives us 1. Again, I to the power of 3 is same thing as minus I. So 4I3 simply gives us minus 4I. Okay, and then I squared is simply minus 1. So 6I becomes minus 6 plus, okay, 4I plus 1. Alright, so minus 4I plus 4I cancels out. 1 plus 1 gives us 2. So you have, So you simply have 1 plus 1, which is 2, minus 6. That gives us minus 4. So this expansion is actually minus 4. Okay. So we simply have I plus 1 to the power of 4 to be equal to minus 4. Now we plug these values into the integral. Okay. So plugging the values into the integral, not forgetting I plus 1 to the power of 3, that gives us 2I minus 2 all over 3 minus I plus 1 to the power of 4. That actually gave us minus 4. Okay, so minus 4 all over 2 plus I into once more I plus 1 to the power of 4. That simply gave us minus 4 all over 2 minus I plus 1 to the power of 3. That gives us 2I minus 2 all over 3. Okay, we have this. Therefore, this is simple as saying 2I minus 2 all over 3. Minus minus here is plus. 4 all over 2 simply gives us 2. So I have plus 2 plus I into, similarly I have minus 4 divided by 2. That gives us minus 2 minus 2I minus 2 all over 3. So we can expand with I. We have 2I minus 2 all over 3. Okay, plus 2 plus I times minus 2 simply gives us minus 2I. Alright, considering this part, I times minus 2I, that gives us minus 2I squared. I times minus 2I over here, this gives us minus 2I, okay, all over 3. You have this. So this is now 2I minus 2 all over 3, okay, plus 2 minus 2I. So this can be, we can break this down. Now we have minus 2I squared all over 3 minus 10. This minus becomes plus 2I all over 3. Okay, so we can also simplify this. This becomes 2I all over 3 minus 2 all over 3 plus 2 minus 2I minus 2. Okay, I squared is minus 1, so you have minus 2 into minus 1 all over 3 plus 2I all over 3. So we have 2I over 3, we have plus 2I over 3. So adding these two, collecting like terms now. So collecting like terms now, 2I over 3 plus 2I all over 3. This simply gives us 4I all over 3. Now I have minus 2 over 3. Okay, this is minus 2 all over 3 plus 2 minus 2I. Now minus times minus here becomes plus, so I have plus 2 all over 3. Okay, plus 2I. That's all. Taken already. I've taken this side already. So we simply have minus 2 over 3 plus 2 over 3. So this actually cancels out. So we simply have 4I all over 3. So we have 4I all over 3. Okay, minus 2I. Bring the imaginary parts together. Now I have minus, okay, I have plus 2. So this is going to be equal to, now the LCM between these two is 3. So this is simply 4I minus 6I all over 3. Okay, plus 2. Alright, so 4I minus 6I gives us minus 2I over 3 plus 2. And this becomes the solution of that integral when y is equal to x to the power of 2. Alright, that's it on that question. I will see you in the next video with another question on Math 305. Thanks and cheers.